Hi, this is Dr. John Bergduff. In this video, we are going to explore some of the most important definitions in all of algebra, and actually in all of mathematics for that matter. And if that sounds a little bit intimidating, don't worry. The concepts themselves are actually pretty straightforward. The applications are beyond number, so we will be talking about these concepts for basically the rest of college algebra and on into many, many courses beyond that. The four topics that we need to explore in this video are the concept of a relation, domain, range, and function. Now we're going to explore three of those basically all at the same time, and then we'll come back a little later and define what we mean by a function. So let's jump right in. What do we mean by a relation? A relation is simply a set of ordered pairs. Well, that sounds pretty easy. Here are a couple examples. This is a set of ordered pairs. There's four of them. 2, 9, 3, 7, negative 1, 5, 0, 5. That's a relation. Here's another one. 4, 2, 5, 9, 4, 7, 6, 8, negative 11, 2. And you might think, well, there's hardly much to that idea. We'll explore it some more. But going along with this definition, I want to look at two other definitions. The first one is domain. The domain of a relation is simply the set of all the first coordinates of the ordered pairs in the relation. Let's explore that with these examples. In the first example, the domain is nothing more than the set consisting of the first coordinates of all these ordered pairs. 2, 3, negative 1, and 0. That's just the first coordinates. The domain for the second example, same idea. 4, 5. Now, if you have a repeated number, there's no need to write it twice, so I don't have to write the second 4 down. I can just go on to 6 and negative 11. And you might ask, is it important to put these numbers in order? And the answer is no. The order of the elements of a set doesn't matter, so you could leave it just the way it is. That's domain, the set of all the first coordinates. Well, even if the definition weren't right in front of you, you probably could guess what the range is. The range of a relation is the set of all the second coordinates. Easy enough. Let's go back to these two examples. In the first example, the range would consist of 9, 7, and 5, the second coordinates, and again, we don't have to repeat the 5, just one time is fine. And in the second example, the range would be 2, 9, 7, 8, and again, I don't really need to relist the 2. Now, when you look at that, you might think, well, this is really very basic, and why is this so very important? It's just some ordered pairs. The interesting thing is we see the concept of a relation all the time in many, many applications. It may just be that the ordered pairs are more or less in disguise. Let me show you another example. Here's a table like you might see in the newspaper at any given time. I have a list in the left-hand column of several cities, and in the right-hand column, what the high temperature was in those cities on the 17th of July in the year 2020. So you can see that in New York City, the high temperature was 84, and in Phoenix, the high temperature was 108. Now, what you really have here are ordered pairs, and you even kind of get the idea of why the word relation is chosen. There is a relation between the first value and the second value. They are somehow connected. In this case, it's the city and the temperature. I could write these literally as ordered pairs. New York City is paired with 84 degrees. Los Angeles is paired with 82 degrees. Chicago with 89. Houston with 92, Phoenix with an incredibly uncomfortable sounding 108, and Philadelphia is paired with 89. The ideas of domain and range here make sense as well. The domain is the first coordinate. We could make a list of those cities, or we could just describe it. We can even just write the domain is the set of cities surveyed, let's say. I might have done a different survey and added more cities, but these 6 cities. And the range is the set of corresponding temperatures. And that would work just fine. So if you think about it, relations occur all the time. Anything that pairs one value with another to show some relationship between them can be viewed as an ordered pair or a set of ordered pairs, and therefore a relation. And you can talk about the domain and the range. Tables are one way to represent ordered pairs in sort of a different way. Let me show you another one. This is sometimes called a mapping. And it's a really great way of really emphasizing the domain and the range. What I have here is a circle that represents 3 men. Maybe these are 3 men in our class, Javier, Tan, and Marcus. And in the second circle, we have their heights, how tall they are. And the arrow represents what is paired up with what. So if I were to make the ordered pairs, or list the ordered pairs, in this relation, I am pairing Javier with 5 foot 10 inches, and I'm pairing Tan with 5 foot 7 inches, and I'm pairing Marcus with 6 foot 1 inch. The domain is the set of first coordinates. Actually, it is also just the elements in that first circle in the mapping. This first circle represents the domain. It's the set of men, maybe men in the class. And the second circle represents the range. That would be the set of heights. Very different relationship and a pairing that's listed in a different way, but the idea of the pairing is there, and therefore the idea of a relation is coming to mind. Here's another one written as a mapping, a little bit different here. In this case, the domain represents a set of men, and the range represents a set of women. The arrow shows pairings, and in this case, let's say that the arrows represent something. They represent who is dating whom. So looking at the arrows and thinking about the ordered pairs that are created here, we have Javier is dating Shonda. We have Tan is dating Becky. And the fact that there's a second arrow there tells me that Tan is also dating Karen. I sure hope Becky and Karen don't meet each other. And finally, we see that Marcus is dating Maria. Ordered pairs represented in a different way, again as a mapping. And the domain and the range are really clearly indicated by the 2 circles, what gets paired with what. The arrow shows the pairing. So that's another example of a relation in a different format. Now, especially important in mathematics, oh, don't look at that slide, it was a bad one. Especially important in mathematics is the idea of representing a relation as a graph. Now, we've seen some graphing already, and we have the idea of getting various shapes. When we look at the shape we see in a graph, it's really, really important to remember that although that does look like a continuous ellipse in this case, what you really are looking at here is infinitely many ordered pairs. Each one of these points on the graph. Oh, excuse me, my pen is being silly. There we go. Each point on this graph represents an ordered pair. And I could write their coordinates. For example, that one I just got to is the ordered pair 0, 4. There are so many points that they essentially run all together, forming what... Sorry, there's a little glitch there. The points all run together, forming a continuous figure, but it's really infinitely many points. Each point is an ordered pair, and therefore this is an example of a relation. Now, talking about domain and range is a little bit interesting because I can't list all of the infinitely many values that I have for the first coordinate and the second coordinate. I'm going to have to think of a more descriptive way. But here's what I can do. If I think of the domain as the set of first coordinates, and I remember that in a graph, the first coordinates are represented along the x-axis, then what I'm really asking for when I'm just asking for the domain is what are all the values on the x-axis that correspond to points on this graph. So for example, if I pick a value of x right here, there is a point on the graph that corresponds to that value of x. It's that point right there on the axis. If I pick a value of x right here, there are points on the graph that correspond to that x value. There are points that correspond to this x value and to this one, and so forth. So the domain is the set of all values on the x-axis that correspond to points. Imagine reading along your axis from left to right, and I'm going to clean this up just a little bit and draw something new. Imagine reading along the x-axis from left to right. If I'm over here at -6, there is no point on the graph that corresponds to -6. There's no point above or below that. That means that is not a part of the domain. The domain, more or less, begins here. This is the first point that corresponds to a point on the graph. From there, all the way to here, along the x-axis, represents x values to which points on the graph correspond. And if you think back to some other things we've done, you realize, oh, that's really like an interval of numbers. And I can write my domain in interval notation. The number on the left appears to be -5, just looking at the graph. So I would say that this graph has a domain that begins at -5 and looks like it ends at +5. The domain is the set of values of x, the values of the first coordinate. What about the range? Well, the range has to do with the second coordinate, and when you're looking at a graph, the second coordinates are plotted along the y-axis. So what we'd be looking for is all values of y that correspond to points on the graph. What do I mean by that? Well, for example, if I pick a y value right here, there are points on the graph that have that y value, this one and this one. That means that this y value, 0, is part of the range. There are points that correspond to that. Similarly, this is in the range. That's a y value, and if you look, there's a point, 2 points that have that y value, and so that's part of the range. Another point up here would not be in the range. There's no point on the graph with the same y value. There's nothing up there. So I think you can see that the range would again be an interval of numbers. Any value of y between -4 and 4 corresponds to some point somewhere on the graph, to the left of it or to the right of it. And so we're going to say that the range goes from -4 to 4, both endpoints included. A little bit tougher idea, but I hope that makes sense. Let's look at a couple more sets of ordered pairs defined by graphs. and focus again on the idea of domain and range. Now, I drew this graph using a program called Desmos, and it doesn't show the arrow continuing on both sides like you would often see, but that's the implication I want to have. This is a line that goes forever to the left and forever to the right. And if I'm thinking about the domain, that gives me an interesting situation. I can see on my graph values of x that are being used all the way from -4 to 8. But if this graph continues on and on and on to the left and the right, that means really that every value of x will be used for some point somewhere, and every value both far off to the left and far off to the right. We can describe that domain as -infinity to infinity. Again, remember, domain is the set of the first coordinates, which in terms of graphing refers to x. The range refers to the set of second coordinates that correspond to points on the graph, or in other words, values of y. And again, these arrows indicate that the graph keeps going up as you move to the left and down as you go to the right. Every value of y is going to be hit somewhere. The range is -infinity to infinity also. Let's do one more to make sure this is clear. This shape is called a parabola. We're going to study these a lot. Again, it's a set of ordered pairs, so it's a relation. Let's focus again on the domain. The implication in my program is that these two branches of the parabola continue on forever. That means the parabola will continue to spread farther to the left and farther to the right. And that indicates to me that the domain of that, much like the line on the previous example, would be -infinity to infinity. The range is different, though. Think back to the ellipse example, and you'll kind of see this. There are values of y that do not correspond to points on this graph. There's one right there. Looking along the y-axis, there is a y value where this graph more or less begins, at its lower end, right here. And the range proceeds from there on up. So it's limited to a degree. The range goes from -4 to infinity. Looks like the point at -4 is included, so we'll put a square bracket on that. And that's the range. We'll explore these ideas a great deal more. Okay, so far we've talked about the concept of a relation, and we've explored the corresponding concepts of domain and range. Next definition, super important. This is one we're going to spend a lot of time looking at, is the idea of a function. A function is first of all a certain kind of relation. So a function is a set of ordered pairs, but it has a special quality to it. A function is a relation in which no two different ordered pairs have the same first coordinate. That's the key thing. All functions are relations, but they're just maybe relations that aren't functions. Let's take a look at basically all the examples we've already seen and see what that would look like relative to the idea of a function. The question I simply want to ask for each question is this relation a function? And guess what? It's pretty easy to see from the basic definition. No two different ordered pairs have the same first coordinate. As I look at these, all the ordered pairs have different first coordinates. That would mean that this relation is a function. Look at the second one, though. Again, a function is a relation in which no two different ordered pairs have the same first coordinate. Look here and here. These two ordered pairs have the same first coordinate. That's not good. That doesn't mean it's not a relation. That simply means that this is not a function. It's not that it's evil or anything, but as we move along, I think you'll see why there's a value to a relation being a function. Let me back up before we go on. I do want to notice one thing about the first example and the second one. Notice in the definition that it says that no two different ordered pairs can have the same first coordinate. There's nothing said about the second coordinate. So if you look at this first example, you'll notice that two ordered pairs have the same second coordinate. There's nothing wrong with that. The only thing that has to be true is that no two ordered pairs can have the same first coordinate. Let's look at some of the relations that we defined in different ways. And the question again is the relation a function? And I think I'll explore a little bit why the definition is so important. Is the relation a function? Do any of these ordered pairs have the same first coordinate? Remember, the first coordinate would be the name of the city. Do any of those cities show up twice? No, they do not. So yes, this is a function. If a city did show up twice, let's say that we just added in here another row that said Houston, Texas, 99 degrees. That would be very peculiar, because what that would be saying is that on this given day, the city of Houston had two different high temperatures, and that would not make any sense. So you can kind of see that a function is a relevant idea. Having a repeated second coordinate doesn't really make sense. Let's look at some others. Remember the ordered pairs that are created. The first circle represents the domain. That's the set of the first coordinates. And the second circle represents the range. Do we have any repeated values of the first coordinate? Do any two ordered pairs have the same first coordinate? And I believe the answer is no. So this is a function. Javier is paired with 5 foot 10 inches, Tan with 5 foot 7 inches, Marcus with 6 foot 1 inches. There's no repeated first coordinate. This is a function. Let's look at this dating example. This is a very good example of how in a mapping you can really see when something is not a function. Remember that Tan was dating two different people, so we had the ordered pairs Tan and Becky, and Tan and Karen. You can see that really, really clearly in the drawing of the mapping, because there are two arrows coming out from the indication of Tan in the domain. This is not a function. And the origin rather of the word function is kind of murky historically speaking. But if you think about this particular example, it might give you some idea of why this word was chosen. If we have Tan dating two different people, that is probably not going to function very well, especially when Becky and Karen compare YouTube accounts and realize they've got Tan with both of them. The mapping version of representing a relation or a function inspires sort of an alternative definition that many people use. It means exactly the same as what we've said before, but it might be useful as an alternative. A relation is a function if and only if each value of the first coordinate is paired with exactly one value of the second coordinate. It's a different way of saying the exact same thing. Here, the fact that you have Tan, one value of the first coordinate, paired with two values in the second coordinate, that's the thing that makes it not a function. And that's the same thing as way back when we are looking at these relations. Each value of the first coordinate is paired with just one value of the second coordinate when you have a function. So that might be useful. Let's look at these relations defined by graphs and see whether they're functions or not. So again, the question is the relation a function? Again, A function is a relation in which no two different ordered pairs have the same first coordinate. In a graph, it is really, really easy to see these. Look at these 2 points, for example. This is the point 0, -4, and this is the point 0, 4. Those two ordered pairs have the same first coordinate, which means it's not a function. And that happens over and over again. This point and this point have the same first coordinate, 4. Now there's 8. This point is only paired with one value, but that's too bad. We already have other ordered pairs with the same first coordinate. So in a graph, you can see this really, really easily. When 2 points have the same first coordinate, they line up right over each other. And when that happens, again, here's another example. 1 point directly over another. Well, let's try this again. There we go. There we go. 1 point directly over another. Those two ordered pairs have the same first coordinate. That means this is not a function. How about this one? Now in this graph, if we look at all the ordered pairs, we don't have the same scenario. I'm not seeing a point on the graph right above another point on the graph. All these points have different first coordinates. We don't have one point right over the other. This would be a function. And how about this parabola? Again, do we see any ordered pairs with the same first coordinate? They'd have to lie right above one another. And I don't think that happens. No two ordered pairs have the same first coordinate. This is also a function. There's a cute little way that people talk about distinguishing a function when you're looking at a graph. And I'll show you how this works as our final observation for this lesson. It's called the vertical line test. And it says this: for a graph to represent a function, each vertical line drawn through the graph must hit no more than 1 point. How does that work? Let's look at these same examples. We already determined that this was not a function. If you imagine just drawing vertical lines through this graph in various places, notice that when you do that, you're hitting 2 points. Sometimes you're only hitting 1 point, and sometimes you don't hit any points at all. But all these places where the vertical lines hit 2 points are points that lie right above one another, and therefore they have the same first coordinate. So we're going to say that this graph fails the vertical line test. And that means it is not a function. On the other hand, this graph, if you draw vertical lines through this graph, you never hit more than 1 point. You only hit one. So you're not seeing 1 point right over the other. You're not seeing points with the same first coordinate. So by the vertical line test, this is a function. So I hope this brief introduction to the concept of relation, domain, range, and function was useful. In future videos, we're going to explore relations that are defined by equations and function notation and other concepts that are incredibly important as well. Hope this is a great start.